Hello, everyone. I'm Sean Buckley, Editor-in-Chief of Lightwave and BTR, and it's my pleasure to welcome you to today's Lightwave and BTR webcast, where we'll discuss getting ready for 800G to 1.6T DWDM optical transport. Today's webinar is brought to you by PacketLight. We thank them for their sponsorship, and joining me today is a great expert on this topic. I'm joined by Koby Reshef, CEO of PacketLight. Welcome, Koby. But before I hand things off to Koby, let me just quickly review our webcast setup and some other housekeeping items. For those of you who may be joining us for the first time or the first time in a long time, I'll start with the Ask a Question box you should see near the slide area. I invite you to feel free to use this to ask questions anytime during the event today. To submit a question, just click in the box, type in your question, and hit the send button. We will address your questions after Koby's finished his presentation. Now, in the event that you run into a technical problem during the presentation, you can call for help via the Q&A tool. Just describe your problem, hit the question submission button, and Milan, who is today's webcast technician, will be happy to help you out. Next, if you know someone who might benefit from seeing the webcast, you just want to revisit the presentation yourself, this event will be available on demand on our webcast archive for the next several months. We'll send you an email with the link to the archive sometime in the next day or so. You should feel free to forward to your coworkers or watch again if you want to take a look at a different aspect. And also the archive version of the webcast will be accessible from the webcast archive section of the website, which you can reach via our homepage at www.lightwaveonline.com. I believe if you'd like, you'd be able to download a copy of today's slides via the Event Resources tab. You should see on the screens right below the Ask a Question box. Just click the tab to reveal the slide files. And with that, with the housekeeping out of the way, let's delve into this really great topic, the evolution of 800G to 1.6T. Koby, the floor is yours.
Thank you very much, Sean, for the introduction and hosting me on this Lightwave webinar. And thank you for the audience for joining. We will go today over the next generation optical network, which are pacing towards the 800 gig and 1.6 tera transport capacities per wavelength. We will go over the challenges, the building blocks, and luckily for us, also on the solutions and the innovations, which will enable us to make this jump toward these high bandwidth demanding networks. The agenda will include some introduction, so why we need so much capacities a bit, and what are the driving forces for us to move into the 800 gig and 1.6 tera capacities. We are going to see the challenges that we have in current networks, which are running 100 gig to 400 gig wavelengths to adapt to these new rates. And we will explore the three main technologies like FlexGrid, L-band, and pluggable modules, which assist us in solving these issues and challenges. And we will also cover other aspects, which are, we see more and more on demand, which is security, using QKD or layer 1 encryption in the optical layer, and network protection and resilience schemes in order to have this large amount of data protected on the fibers and on the network. So first, what are the challenges that I'm sure all of you are meeting in your day-to-day life? The bandwidth, the capacities. We need more and more capacity over the fibers. We need to have it very efficiently at low cost. Some of the networks are still traditional rigid networks with fixed grid capabilities only. And we would like to have our data more secured, or the demands for security also increases over time, and we need to meet standards that force us, whether in the medical area, financial, fintech area, or government entities and so on, that need to protect the data which is passing between data centers. So in order to meet that, we need to increase the bandwidth and find ways to have more capacity in the same fiber. We need the network to be flexible and scalable, so it can migrate from 400 gig to 800 gig, 1.6 tera, and maybe 3.2 tera in a few years from now, without replacing the network or the main components in the network. We need to enhance more security into our network against tapping, against extracting the data from the fiber. And we will explore the solutions and technologies which will shape our future networks and their capabilities. What forces us to use or move forward with the rates of the wavelengths from 100 gig to 200 gig to 400 gig, 800 gig? It looks like an endless race. The race is mainly driven by the applications or the capacities and the demand for more and more capacities out of the fibers and the network. One of the main leading bandwidth capacity applications which will really explode the bandwidth of networks will be the AI. The AI requires a huge amount of data to be transported between data centers, and this will increase the capacities of the fiber optical networks and will push us for more and more bandwidth and solutions to find ways to achieve more capacity from the fiber. We need to deliver the services fast, so we need fast turn up of new services. The customers don't have much patience, and they would like the circuit running after one. Either if it's an internal circuit within your own organization, or you are a service provider providing the service to an entity or DCI customer, you will need to turn up the services faster, at least, than your competitors. We don't want to change the infrastructure, the ROADMs, the amplifiers, the fiber infrastructure, the layer 1 infrastructure. Every time there is a new need for more capacity in the fiber, we want to utilize and increase the network organically without replacing things. So we will be able to adapt to new rates, new capacities, without changing too many stuff in our network. There is very limited rack space resources in data centers. Hyper data centers are being built everywhere now. It requires a lot of real estate. It requires a lot of power. And both power consumption and rack space are the main issues in data centers today, and we need to keep them very efficient. So we need to decrease the rack space. We need to find more compact solutions to have more capacity, and we need to decrease the power per bit on the transmission. So moving from 100 gig to 200 gig to 400 gig and so on to 800 gig and above will improve the power per bit transmission, and will reduce the rack space within the data center that the optical transmission equipment consumes. And we need to keep the cost down. We need to improve our cost. There is an enormous pressure about the cost per bit, and we need to keep the cost per transmitted bit lower and lower. All these factors are the driving forces driving us to migrate from 400 gig to 800 gig, 1.6 tera, and 3.2 tera in the future. All this advancement in the capacity per wavelengths make the network more efficient, less power, and more compact, and accommodating for the increase of bandwidth which is needed. Just an illustration slide which shows how much the data has been increased over the last 20 years. So going back to 2000, we spoke about sub 10 gig wavelengths, like wavelengths of 1 gig or wavelengths of 2.5 gig. The max capacities or the capacities we could achieve within a fiber are less than 100 gig. Later on, the 10 gig came along, and we can tenfold. We increased the capacity of the fiber tenfolds. Then the 100 gig, and again, we had a jump of tenfold capacity inside the fiber, and we could reach about 10 terabit per second inside the fiber. 200 gig, double the capacity. 400 gig, just increased 25% more capacity out of the same fiber. And 800 gig will enable us, using the L-band, also to double the capacity again of the fiber. So all this advancement, one point to note is that there was a really revolution in the optical transport network with the invention of the coherent technology, which is a digital signal processor used for processing the optical signal. It enables us to have modulations and improve significantly the spectral efficiency of the network, remove dispersion compensator modules from the network, as we could, the DSP can solve the dispersion compensator digitally using the processor. And from this point, really the advanced from 100 gig, 200 gig, 400 gig, and so on was enabled. What we see in the last few years is that it's tricking that the time that each technology comes and helps us to provide more capacity within the fiber decreases. So if it was like more than 10 years for the 1 gig, about 8 years for the 10 gig, now we are speaking about range of like 3 to 4 years between technology and technology. So the time is shrinking. The innovation is very high and running very fast. And it's from one hand, it's very exciting. On the other hand, it's very challenging to accommodate all of that, to build the new systems, accommodate the new rates, and answer the hungry bandwidth demanding application out there. In this slide, I wanted to show you how much rack space, power consumption, and capacity how you needed back then, let's say in 2007, when we needed 800 gig capacity inside the fiber, we needed to run 80 wavelengths of 10 gig. We needed, it can be 8U, can be 10U, can be 12U of equipment in order to have 80 wavelengths. It means 80 lasers, 80 receivers, very high power consumption, a lot of wavelengths to manage, and the total capacity we could achieve is around 800 gig. That's it. Then, as you remember, the evolution of 100 gig, increasing 10 times the capacity. But more than increasing the capacity, it's also saving a lot of wavelengths. We need just 8 wavelengths in order to run 800 gig using 100 gig capacity per wavelength. We need less devices, and we need less transceivers and less receivers. So 10 times less wavelengths, less receivers, less transmitters in order to achieve 800 gig, and we can have more than 10 times the capacity than we could have in 2007, meaning something like around 8 to 10 tera capacity inside the fiber in 2012. These days, we are launching the 800 gig platforms. And in 800 gig simple 1RU platform, we can achieve a capacity of 8 tera. So we can achieve all the huge amount of devices, many wavelengths needed in the older generation. We can compress to a very small footprint device with much more capacity. So power consumption, rack space, all the issues that are the challenges, the main challenges in data centers and carrier networks have been reduced to small dimensions with less power consumption, enable us to meet the new high demanding application. So there is a really big steps in the equipment, the rack space, and the power consumption as we go along the years. I'm now going to go over some technologies which enable us to mitigate the current networks, which are sub 800 gig, let's say, up to 400 gig, moving forwards toward the 800 gig, 1.6 tera and beyond. So all of that is for doing that, a flex grid technology, which enables us to look at the spectrum at the C-band. C-band is the spectrum of inside a fiber, which we are using for transmitting the DWDM, the dense wavelengths division multiplexing wavelengths. The C-band used to be split into channels, into fixed channels, fixed grid channels. We call them channels like channel 28, channel 29, and we could have around 96 channels at 50 gigahertz spacing, 48 channels at 100 gigahertz spacing, and so on. But the channels were fixed. And the capacity of the fiber, or the spectrum of the fiber that used for transmission, the C-band, was divided into fixed grid of wavelengths. Going forward, we will see that moving to flex grid enable us to look at the spectrum of light inside a fiber as slices of spectrum rather than fixed channels. And this is the secret behind aligning 100 gig and 800 gig and 1.6 tera wavelengths efficiently inside the fiber and utilizing the fiber to the best. Some challenges in moving to the flex grid, especially if you are in a brownfield network with existing network. Some of the infrastructure components will need to be upgraded, like ROADMs, passive max demaxes, and so on, in order to operate in slices instead of fixed channels. The network management tool, which used to look on the network as a pool of wavelengths at fixed grid, now needs to look on the entire network, entire infrastructure, whenever it's a ring, mesh, linear add and drop, and so on, as slices of spectrum. So when we assign a new service, the spectrum that will be assigned to this service will be at the bandwidth of 800 gig or 1.6 tera or 100 gig, depending on the type of service that we would like to pass over our network. The coherent modules, the optical modules in the network, instead of tune them to a fixed grid wavelengths, like channel 28, channel 29, fixed grid spectrum, we will align them to any wavelengths, any, let's say, frequency that we need to adapt to. And around this frequency, the bandwidth of the signal will determine the capacity that we need. So the tuning of the wavelengths is very, very flexible, and they need to support it. So all the optical modules need to support it. So in general, you can see that the entire ecosystem of the network is being adapted or needs to be adapted to work on a flex grid mindset or flex grid components. To explain a bit more the flex grid and what it brings to the network and why it's needed when we are moving into 800 gig and 1.6 tera wavelengths, I will go over this slide and show you step by step how a fixed grid looked like. And I took as an example wavelengths from 100 gig to 400 gig, which are the most popular wavelengths today in the network. So if we speak about 100 gig and 200 gig wavelengths, typically they could fit into 50 gigahertz spacing filters. When we go to 400 gig wavelengths, we needed either 75 gigahertz spacing or 100 gigahertz spacing filters. We need the filter of the wavelengths, or the capacity of or the spectrum slice of the wavelengths need to be at 100 gigahertz spacing. It's still reasonably to use 100 gig, 200 gig, 400 gig on a 75 gigahertz grid or 100 gigahertz grid spectrally. But now look what happens when 800 gig wavelengths is coming to play, and we want to place it also on the same fiber. The 800 gig wavelengths consume 150 gigahertz spectrum slice, twice the capacity of a 400 gig slice. And if we align them together on the same fiber, it means at a fixed grid channel alignment, it means that, look on the 100 gig channel, we need to provide it 150 gigahertz slice of spectrum. It's very, very inefficient because we could put 8 times the capacity on the same slice using 800 gig channel. So in order to have this diversity, this variety of different wavelengths with different capacities of wavelengths, this is what the flex grid does. it enables us to condense all the wavelengths running on the fiber and make the fiber spectral efficient. We do not need to have the 100 gig channel occupying 150 gigahertz spacing slice of spectrum. We can align it to the 50 gigahertz spacing. So we will align 150 gigahertz spacing for the 800 gig. We will align allocate 75 gigahertz spacing slice of spectrum to the 400 gig, and only 50 gigahertz spacing for the 100 gig and 200 gig wavelengths. And this is how spectrally we keep our fiber very, very efficient and carrying as much more capacity more efficiently. When 1.6 tera wavelengths will appear, if they will consume probably around 200 gigahertz spacing, we can align another wavelengths, which is a 200 gig capacity wavelengths. So it can coexist with the 800 gig, 400 gig, and the existing 100 and 200 gig. The nice thing about it is that you don't need to change your infrastructure. So if you are prepared for FlexGrid, you don't need to throw away existing infrastructure. You can keep the pace of wavelengths capacity while maintaining your existing investment in the different optical devices that you have, or cards. So to summarize the FlexGrid, we can, using this FlexGrid methodology, we can support different channel sizes. We can accommodate all the new on the same fiber and the future as well. We increase the spectral efficiency of the fiber with less replacement of equipment. And we see it very, very oftenly in data centers interconnects, mainly predominantly now in the AI, where they need a lot of capacities. Metro networks that you want to keep growing and adapting for new rates without replacing your entire metro network infrastructure of a carrier or service provider. So you can adapt for the new rates, be more efficient, deliver more bandwidth in less power consumption, cheaper, without replacing the investment that you already did in your infrastructure. And of course, in long haul and submarine networks where bandwidth is very, very precious. So we see a lot of, actually all the high bandwidth demanding or long haul networks or metro networks or high capacity DCIs benefiting from this FlexGrid ability. Additional trend that we see going forward and increasing the fiber capacity and bandwidths, decreasing the cost per bit and so on, is utilizing additional band in the fiber. Today, we operate, most of the DWDM systems in the world operate at the C-band spectrum. Why the C-band is used for optical transmission is mainly because the attenuation of the fiber in this range of wavelengths or frequencies is less. So we can go farther with using less amplifiers, less OSNR, and so on. So the best performance of the fiber in terms of attenuation is in this band. All the transceivers, optical amplifiers, ROADM, in most of the networks around the world are built for the C-band spectrum. What's the issue that we are facing with the C-band? Is that the C-band is getting exhausted. Why it's getting exhausted? You can see that to transport 64 wavelengths of 400 gig that we can have in a C-band, we can map 32 wavelengths of 800 gig on the same C-band fiber. So the same capacity. Yes, the 400 gig will require 64 wavelengths instead of 32 wavelengths, but in terms of capacity, instead of throughput of the fiber, we got to a limitation. So moving from 400 gig to 800 gig will not increase our bandwidth of the fiber. And if we want more bandwidth, we need to find an alternative solution. So the alternative solution is to find another band spectrum of light inside the fiber, which is called the L band, which is also suitable for transmitting DWDM over long distances over fibers, and building an ecosystem for it. So we need to develop ROIDMs for it, optical amplifiers for it, the maxes, and optical transceivers for this new range of frequencies. But using this new range of frequencies, we can double the fiber capacity. So the C-band exhaustion, despite the fact that we are going to higher bandwidth wavelengths, we got to a point where the higher bandwidth wavelengths will not increase the capacity, and the L band is being utilized. So again, if we look on the slide, we can see the C-band and the frequencies which compose the C-band, the frequency, the spectrum which compose the C-band spectrum. As I mentioned, we can map 64 channels of 400 gig, which is 25.6 tera. It's huge amount of capacity, but still there are applications out there that requires more. We can, on the same fiber, have alternatively 32 channels of 800 gig and have the same results of 25.6 tera. So moving from 400 gig to 800 gig, we got to a limitation of the bandwidth. Yes, we use half the number of transceivers, so we can build more compact devices. We can use less lasers, less receivers, so less power consumption, but capacity remains the same, which is a problem. The L band will enable us to utilize another 32 wavelengths, let's say of 800 gig, so we can have another 25.6 tera. So we can double the fiber capacity. So mixing C-band and L band together and having wavelengths or transceivers, amplifiers operating along all this range of wavelengths will double our capacity inside the same fiber. We will not need to lay another fiber or rent another fiber, and we can double the capacity of the fiber. This diagram illustrates some of the ingredients in order to build C-band and L-band type of solution. It's very simplified for point-to-point DCI solution, but the concept is that in this slide I took an example existing system which is designed for 400 gig, which got to the max capacity of 64 wavelengths of 400 gig or 25.6 tera. This upper side is operating in a C-band spectrum, the traditional most used spectrum, and with the addition of C-band splitter, an additional L-band max, and L-band amplifier, and L-band transceivers building the transponders, you can double and align the C-band together with the L-band and run them over the same fiber between the two data centers and double your capacity to meet your needs. So this is a bit about the ecosystem: new transceivers, maxes, amplifiers, the red-blue splitter, and then you can achieve your full 51.2 tera capacity. There are some challenges on building C plus L band. Some of them are building long haul networks like that, or a few inline amp, because you will need to. There are some interference between the C band and L band channels, and there are ways to mitigate it, but it's not as simple as the only C band days. But these are all technology aspects that are or challenges that we know how to solve and know how to build a network. Another part of the network which enable us making more compact and higher capacity devices to achieve the goal of the power per bit, the price per bit, and the density of the real estate, is using the pluggable optical transceivers, which have been adapted widely. There are MSAs, they are based on MSA standards. So typically now we have multi-source for each one of them. They are interoperable with each other. So the standards are set. They enable us a pay-as-you-go architecture because they are pluggable. We can start with 800 gig, then another pluggable module, another 800 gig, so we can grow the capacity and use the power and light up more wavelengths as we need more capacity. And really they are the one of the main building blocks able to support C-band and L-band, achieving this high density 8 tera 1U type of solutions. The other aspects, which are kind of parallel, they also exist in the 400 gig or 200 gig networks, but the awareness for them is growing year by year, at least from what I see, is the encryption. More and more requirements are to encrypt the data between data centers. Not always an enterprise customer, a bank, or others knows if someone taps the data of the fiber. If you just bend the fiber in the middle and extract 1% of the light, you can have 100% of the information passing in the fiber. There are a lot of regulations for the healthcare, for the financial market, government, and any credit card company, insurance companies, that they need to keep the data safe. In order to keep the data safe, the optical networks offer layer 1 encryption. Layer 1 encryption, the difference between layer 1 encryption and IPsec or MACsec that can be used is that the layer 1 encryption maintains the full throughput of the data. So there is no overhead per packet. We are not adding overhead on packets. We are not reducing the bandwidth of the service due to the encryption. We maintain full transparent rate of the service while encrypting all the data without any omissions. It's done in a very low latency, so all latency sensitive applications can benefit from it. And we also know how to detect fiber degradation on the optical layer, which can hint to fiber tapping or possible changes or fluctuations in the fiber, which is also very important, which is not something you can see in the IPsec or MACsec layers. The encryption is done with AES 256. Typically a different machine per each port, so you can encrypt per service or the entire uplink, the entire wavelength. And the last additions and enhancement to this layer 1 encryption is also use quantum key for the encryption. So we have added ability to connect to quantum devices which pass the keys on a dedicated fiber Q channel that can't be tapped. So the keys between the two sites are passed over a quantum channel. So it's even safe against quantum computers. Quantum computers cannot break it, as people fear that in few years there will be quantum computers that will be able to break the Diffie-Hellman key exchange. So the keys are being passed between the two quantum devices, and the WDM equipment at both sides extract the keys locally from the quantum device without passing them using the Diffie-Hellman over the DWDM link. And this ensures a quantum level of encryption for all the data passing between the data centers. So even for future threats, as the quantum computers, there is already a solution which can be easily implemented in the optical transport layer. So in terms of the quantum key distribution, it's really very immune about any for conventional fiber, any conventional fiber tapping. It's ready for the quantum computers, and it pairs very, very well with DWDM. There are still some challenges in the quantum. It's relative new technology, or it's becoming, there are more and more vendors in this ecosystem. Still, the cost is high. The distance is limited, so the Q channel distance is limited. And there are no mature standards yet. So if for example, we need to pass FIPS and common criteria with the layer 1 encryption and with our optical devices, there are no standards in FIPS or common criteria for the QKD devices. I assume it will be solved and people are working on it, but this is one of the adoption issues for the quantum key. The last aspect in my presentation is protection. Protection is very, very essential. The capacity, the fibers that we are using today transport enormous amount of data. Any drop of fiber or any drop of equipment can cause large damages. If you are an online betting company, or you are a TV station, or a credit card company, or a bank, if you lose your connectivity, it means you have, or you are a carrier, it means that you have many, many unhappy customers. Downtime can be very, very, very hurtful. So there are two common, there are few protection schemes. I cover here only two of them as an example. There is a full equipment and facility protection, which includes double the equipment and double the fibers between sites. Typically, the fibers are being routed into two diverse paths, or you are taking the fibers from two vendors or two carriers or two service providers in order to ensure if one fiber or one carrier will have an issue, you will have the alternative path. So any failure in equipment or any failure in fiber, you still have your data safe passing between the two sites. Today we also, in this type of applications, we put inline OTDR, so we measure the fiber attenuation. We in case of fiber cut, we immediately know to detect if the fiber was cut or there is some malfunction in the amplifier or the transceiver and so on. So these are the tools, diagnostic tools that we use in the network as well. And the last example of fiber path protection, from experience, we see that 90% of the cases of loss of communication between the two sites is the fiber cut. And in this slide, you can see facility protection. Facility protection, we use the same equipment, but we transport all the data in two diverse fiber paths. So upon fiber cut, in less than 50 milliseconds, which is hitless to the layer 2, layer 3 protocols, we can switch over and maintain the traffic between the two sites. The advantage here is the cost. We don't need double the equipment. We don't need double the transceivers. But we protect only facility, meaning only the fibers between the two sites. So again, based on the budget and based on the SLA, there are different methodologies that different customers adopt over the fiber. Going through the summary. So we explored the flex grid, the L-band technology, which help us to have more and more capacity, more data, more efficiently, maintaining the existing infrastructure and be ready for the 800 gig, 1.6 tera and above. We saw the pluggable modules and their role in all this ecosystem, achieving a higher density, lower cost, standardization, encryption, which is very important to protect and keep the data safe. All our data is passing between data centers. We don't want any access to it by anyone. And the protection in order to maintain a healthy network and resiliency against fiber cuts or equipment failure. All of those will help us to go ahead and build very efficient 400 gig, 800 gig, 1.6 tera and above transport network, which will last for the next decade and hopefully will serve well all our customers. Thank you very much for listening for the presentation, and I will give Sean back the speaking.
Yeah, yeah, it's a lot of, I mean, there could be like 20 other webinars we could do. Lots of great stuff here. And, you know, like I said, some things that we discussed at ECOC. But anyway, I'll just start going through some of the questions here as we have them. All right, let me just pull this out. All right, let's see here. One is using coherent technology. Will that solve many problems related to dispersion? Should we continue measuring CD and PMD for future high-rate optical networks? I think you might have talked a little bit about that. A lot of
Yes. So chromatic dispersion was used to be in order to accommodate for chromatic dispersion in the 1 gig, 10 gig. We use the special devices called the DCM or DCF, fiber dispersion compensator fiber, or dispersion compensator modules. When going to the coherent transceivers or the DSP, all this compensation of the chromatic dispersion is done by the DSP. DSPs today can do, for example, over 1,000 kilometer of or 2,000 kilometer of chromatic dispersion compensator digitally. They detect the fiber length, they detect the chromatic dispersion, and they compensate for it while doing the acquisition or the digital signal processing on the signal. It's really a great way. They do it, we can report it, and when you know more or less the chromatic dispersion that is measured by this optical module or the DSP compensation software or processing inside this DSP, you can actually more or less guess the distance of the fiber, the length of the fiber, if you divide it by the 17 or 18 picosecond nanometer to kilometer of the fiber chromatic dispersion parameter.
Great. Here's a couple questions about the L-band. I'll start with this one. The question is there specialized fiber that reduces the attenuation in the L-band? I know that was a big part of your presentation, yeah.
I must say that, to be honest, I'm not sure if there are dedicated fibers for L-band.
Right.
What we want to use mainly is to use the same fibers that we already have in place without putting new fibers, and utilize the L-band together with the C-band. So the C-band typically on the existing infrastructure is already in place. We now want to use the L-band, and then the G652 fibers, it's possible to do that. We don't need special fiber for that. Maybe there are planned to be unique or special fibers for the L-band, but they need to support also the C-band as well.
Okay. Here's another question about L-band. You kind of, it's a really interesting discussion follow up on here. Will L-band equipment cost a premium over C-band equipment? And the question goes on to ask, is there a situation possible where getting a second fiber pair and using the C-band on it again is cheaper than to start using the L-band on the first pair? A lot to unpack there. Yeah.
Yes, I think the answer is on a case-by-case basis. It might be easier and simpler to use additional fiber to people which have the ability or access to additional fiber. It may be better to put additional fiber for the C-band. So that's, in certain cases, it's easier. But if you are renting a fiber of 200, let's say 100 mile or 150 mile, and now you would like to rent another fiber of 150 mile, it may cost you a monthly fee more than the fee to have the L-band running on the same fiber and utilizing also the L-band of the fiber you're already renting and paying for. So I think here you need to see how much costs you to have another fiber compared to how much it will cost to add L-band to the existing fiber. So that's I think that it can go either way, depending on a case by case. The L-band component, just on the L-band is more or less starting, so the quantities there are less. L-band amplifier, for example, is bigger in dimension and size compared to a C-band amplifier. So it's also currently it's a bit more difficult, may cost a bit more, but not double the cost or not a high amount of cost. So there are challenges. I believe that as the technology will be more maturing and more used and utilized, the quantities will increase and prices will decrease to the same level of the C-band prices.
Okay. This next question is, do your capacity per channel numbers include overhead for forward error correction, which can be as high as 25%?
Yes, the capacities that I mentioned include the forward error correction. So when I speak about placing 64 wavelengths of 50 giga let's say here, like 64 channels of 400 gig at 75 gigahertz spacing, it's including the overhead of the FEC. So we need 75 gigahertz in order to accommodate for the FEC. Now, there is one thing here, if you want to go to ultra long distance or very long distance, so the modulation that we use for the 400 gig will consume more bandwidth. So we will need to go to 100 gigahertz spacing or even 125 gigahertz spacing if we would like to go to 2000 kilometers with 400 gig. So in this case, we change the modulation. So instead of using 75 gigahertz filter, we will need to double the filter bandwidth in order to accommodate for the extra performance or the FEC and the modulation which are needed. So instead of QAM16, we will go to QPSK with 400 gig and consume more bandwidth spectrally, but we'll have better FEC and better performance.
Okay. Here's a little bit of a forward-looking question. It's asking, how much time do you think it will take the industry to have 800G to 1.6T as the standard for fiber communications? Again, everything's an evolution, as we all know, from 10G to even a gigabit, as you and I probably saw 20-something years ago. But anyway, yeah, just, I guess, seeing what the horizon is. Yeah.
Marketing-wise, it should have been sold for 2 years already. Practically, right. Practically what we see now, the transceivers are there. So there are few transceiver, the DSP is there, it's working. There are the ecosystem of the transceiver vendors is there, and they are going to be GA'd in around March, June timeframe, depending on the different vendors. But at the first half, let's say, of this year, there will be pluggable coherent modules in the form factor of OSFP, QSFP-DD, or CFP2, which are will be available in GA state. And this is the main building block that will enable us to build the network, because the amplifiers we have, the ROADMs we have with FlexGrid. So the transceiver issue with the latest DSPs will come to market by June timeframe in a GA state that you can buy large quantities of and deploy. So I believe the first deployments will start second half of this year, practically. Still, the cost is high because the technology is very new. So it will take time to drop in price. So I would expect now to have 2 wavelengths of 400 gig at about the same cost as 800 gig, but you will save again spectrally, and going forward in a year from now, year and a half, the 800 gig will definitely cost less and consume less power, and improve all the parameters that we spoke of.
Great. Here's kind of a question on, again, some of the exciting stuff coming down the pike. If the dark fiber is used to send a quantum key, does it not mean it's no longer dark and thus can be accessed to compromise the security? I know you did go over encryption and you mentioned QKD, yes. But yeah.
So the Q channel, unlike DWDM or wavelengths that we use, is sending few bits with different phases. The bits that are being sent are really, how I describe it simply, it's very low number of bits which are being transmitted at different phases. It's impossible to detect them. So if you bend the fiber, you already the receiver on the other side of the data will feel that something really terribly happened. It's very sensitive due to the fact that we are sending very few bits to signal every very few photons, in order to symbolize a bit. And these photons are so sensitive and so few that it's very easy to detect if someone even bent this type of fiber. Immediately, the other device will feel drop in the bandwidth of the keys it can get and alert about fiber tapping.
Right. Okay. Let's see. Here's another thing, and I think you kind of addressed this about on kinds of fiber, but as many of us are transporting over aged or fiber, we do pay more attention to PMD than CD-based technology you mentioned. But is there a limit to PMD where you would see a red flag? That's the question.
So far, from all our experience, we haven't met a fiber with a PMD in a level that we cannot pass the coherent wavelengths on top of it. We didn't experience issues around the PMD on all the fibers that we transported. There are some limitations of PMD. Each optical transceiver or each technology and each DSP can mitigate for a certain amount of PMD. It's not something that I saw challenging, but maybe I haven't seen all the fibers in the world and all the cases. But typically, you don't meet it. I didn't find, and we deployed over thousands of links and everywhere around the world. And
yeah. No, for sure. I mean, where are you seeing this sweet spot here? I mean, obviously, everybody's talking about data center interconnection. I think you even mentioned to me 1.6T coming into subsea stations. I mean, that's a big market too. I would imagine your products, have good fit into these types of environments where you have, a cable coming into New Jersey or wherever it may be, some in Miami, I guess. I mean, what are some of the key applications that we'll see?
A lot of the things that we see now is that the subsea cables have more and more capacities and more bandwidth.
Right.
More and more subsea cables are being built, and actually carriers are connecting over these subsea cables from one side of the ocean to the other. And each side of the landing stations, they need to distribute the data to their POPs. And the capacity of this data increases. And it can be a few miles, or it can be 100 miles from the landing point to the main POP of the service provider need to be connected inland. And we see a lot of applications recently for this connectivity. A demarcation point at the subsea cable line and another demarcation point at the POP of the carrier or the customer, using renting some data from the subsea cable or some wavelengths or some capacity from the subsea cable.
Right. And another great point that I think you brought up, just not to switch gears, but it's you talked a lot about visibility. I thought that was kind of interesting. I think that's going to be a big thing for people as we start to scale. So yeah, great. Well, we're almost about out of time. So maybe if Koby, you could take a minute or two just to give us some final thoughts, and we could wrap up the webinar. And I could thank you for another education here. So yeah.
So what at least we recently met at PacketLight is really the unimaginably high bandwidth that AI application require. We are speaking about multi-terabit per second on a fiber.
Right.
And this enormous capacity is needed will drive all the optical market. It's really like a new age for the optical market. It's not the traditional applications that we accustomed doing, an increase of bandwidth and so on. It's gigantic leap in the bandwidth that will be required. So I believe the pressure to have more and more capacity, more and more innovation, more and more density inside a fiber will continue, and this is very exciting for me because it's not boring. Everything is really exciting.
That's
we need to run. We need to increase the capacity. We need to find more and more ways to do that. And I think really it's really high-end innovation. All this WDM transmission, optical networking is really leaping in huge steps of intelligence, of abilities, and it's very exciting.
No, for sure, for sure. No, I mean all the things that that we have regular talks with PacketLight about, whether it's moving to 800G or the quantum stuff. I just think there's a wide area of things to explore, and I think we got some really good questions today too. So I want to thank the audience and thank Koby for another great presentation and webcast. And again, to remind everybody, if you want to take another look at the webcast, you can certainly do so at your leisure. I mean, I think there's some really great insights we got today. And I want to thank Koby for bringing those insights to the webinar, and again, to the audience, and of course, PacketLight for being our sponsor today. But thanks very much. And I hope everybody has a great afternoon. And yeah, thank you. All right, great.
Thank you very much for joining and hosting me, Sean.
No problem. Thank you.